August 5th, 2026. 35 minutes past 2 in the morning, Eastern Time. Across the Americas, telescopes are pointed at the same spot, the western edge of the Moon, near a crater named Einstein. 3 professional observatories have allocated time for this. 2 spacecraft in lunar orbit have adjusted their observation plans. At that second, something hit the Moon at 5,400 miles an hour. Within hours, fake footage of the impact was circulating online, which tells you roughly how much real footage there was. Now, this was not a failure of equipment. There is a reason nobody could have caught it, and that reason has been true for as long as anyone has been watching. Since 1999, several hundred impacts on the Moon have been recorded through telescopes. Apollo astronauts saw them from lunar orbit. The Artemis II crew reported seeing them during their flyby earlier this year. Every single one of those detections happened on the dark side of the Moon, the unlit half, where a spark stands out against black. No impact flash has ever been detected on the sunlit face of the Moon, and that is exactly where this one landed. So, somewhere on that bright edge, there is now a fresh hole in the ground, and a blanket of material around it that had been buried since before there was anything on Earth to bury it. 2 days later, no human being has laid eyes on it. Start with the strange part. We missed it, but we knew it was coming 11 months in advance, down to the second. September 2025. A piece of orbit computing software finishes a run and returns a date. The software belongs to a man named Bill Gray, who has spent decades writing tools that astronomers around the world use to work out where things in space are going. Asteroids, mostly. Comets, occasionally something we put up there ourselves. The program does one thing very well. It takes scattered points of light recorded by telescopes on different continents on different nights and works backwards to a path. This time the path ended. It ended at the Moon, at a specific hour, on a specific patch of ground. A prediction like that is not the same as a certainty, and Gray said so himself at the time. It looked solid, but he couldn't be totally sure of it. And there was a reason for his caution that had nothing to do with mathematics. 4 years earlier, he had made almost exactly the same announcement about almost exactly the same kind of object. A spent rocket stage, he said, was going to hit the Moon. The press ran with it. Then, closer analysis showed that the thing he had been tracking wasn't what he thought it was. It was Chinese hardware, the upper stage from the Chang'e 5T1 mission, and it struck the far side of the Moon in March 2022, where nobody on Earth could watch it. So, in September 2025, sitting on a prediction that would eventually make headlines on 4 continents, Gray was careful. This time, he said, there was no doubt. This object had been tracked since launch. And that is worth holding on to because it makes everything that follows stranger rather than simpler. This was not a surprise. This was the most precisely predicted unplanned lunar impact anyone had ever had. NASA's Center for Near-Earth Object Studies eventually confirmed a 100% probability of impact. We had the date. We had the coordinates. We had almost a year to prepare. January 15th, 2025. A Falcon 9 lifts off from Kennedy Space Center carrying 2 robotic landers toward the Moon. The first is Blue Ghost Mission 1, built by Firefly Aerospace, flying under NASA's Commercial Lunar Payload Services program. The second is Hakuto-R Mission 2, a lander called Resilience, built by the Japanese company iSpace. The rocket does its job, and then it comes apart into 4 separate tracked objects. The first lander is catalogued 20-25-010A. The second is 10B. A payload canister is 10C. And the upper stage of the rocket itself, the piece that pushed everything else out of Earth orbit and onto a path that could reach the Moon, is 20-25-010D. That designation is not a name, it's an address. It says this was the 10th rocket launched into orbit in 2025 and the 4th piece of hardware tracked from that launch. nothing more. The four pieces then went in very different directions. Blue Ghost landed on March 2nd, 2025, the first fully successful commercial lunar soft landing anyone had achieved. Resilience took a longer, fuel-saving route and attempted its landing on June 5th. Contact was lost about 90 seconds before touchdown. It crashed. A later technical analysis pointed to a problem with its laser rangefinder. The payload canister came down through Earth's atmosphere on March 15th at 6 minutes past noon Universal Time, near the border between Argentina and Chile. If anyone happened to be looking up, it would have appeared as a fairly bright meteor. Gray has said he doesn't know whether anybody actually saw it. That phrase is going to keep coming back. The fourth piece stayed up. Normally, a Falcon 9 second stage is disposed of by letting it fall back into the atmosphere and burn. But this had been a high-energy mission, the kind that flings its payload most of the way to the moon, and once the stage had done that, it no longer had the fuel to come home or to push itself out into deep space. According to SpaceX, a mixture of solar activity and gravitational forces took over from there. So for a year and a half, it went around and around, in a long, lopsided orbit, in the same gravitational neighborhood as the moon. And here is the thing about that year and a half. Nobody ever saw it either. Not really. This object is 12 to 14 meters long and about 4 meters across, roughly the height of a 5-story building. At the distances involved, no telescope on Earth could resolve it as anything but a dot. By February 26th, 2026, there were 1,053 recorded observations of 20/25/010D, 1,053 points of light. The most detailed picture anyone ever got of it came from watching that dot flicker. An observer in the United Kingdom named Grant Privet took a 12-minute exposure in which the object visibly brightened and faded 5 separate times. Another observer, Jean-François Gu, produced a light curve tracing the rise and fall in brightness over a little more than 3 minutes. That's the entire visual record of the thing, a dot getting brighter and dimmer because a cylinder was rotating in sunlight a couple of 100,000 miles away. And that flicker mattered, because how it tumbled determined how sunlight pushed it, and how sunlight pushed it determined where it would land. Now, the obvious question. If the collision was predicted 11 months out, why did nobody move it? The answer is not engineering. It's absence. There was no engine burn coming, because the stage had no fuel left. That was the entire reason it was still up there. There was no command to send, because it had no radio. And there was no mission being prepared, because no such mission exists anywhere on this planet. No agency, no treaty, no office in any government holds the assignment of managing dead rockets in the space between the Earth and the Moon. Compare that to the space closer to home. Low Earth orbit has collision avoidance procedures, conjunction warnings, debris catalogs updated constantly, and real pressure on operators who leave hardware behind. The International Space Station has maneuvered a few dozen times to get out of the way of things, cross an invisible altitude line, and all of it evaporates. For 18 months, the sum total of humanity's monitoring effort on this object was one contractor's software and whatever the asteroid hunters happened to catch by accident. Nothing about August 5th could be stopped, and nothing was trying. We are extremely good at tracking space junk. The US military does it with radar, and it does a superb job. Over the years, they have tracked gloves and tool bags that astronauts lost. But all of that works in low orbit. 20/25/010D was out at lunar distances roughly 400 times further away. And radar does not degrade gracefully over that gap, it collapses. If something is 400 times further away, it receives only a tiny fraction of the transmitted energy, and only that same tiny fraction of what it reflects ever comes back. Apply the loss twice, and the return signal from something at lunar distance is around 25.5 billion times fainter than the same object in low orbit. Radar is superb for close things. For distant things, it is simply blind, which leaves telescopes. And this is where the story says something quietly remarkable about how this kind of science actually happens. Nobody was assigned to watch this object. There is no agency whose job it is to track high-altitude junk. What exists instead is a global network of asteroid surveys, telescopes, whose real mission is planetary defense, hunting for rocks that might one day hit Earth. From their point of view, time spent looking at junk is time not spent finding rocks. They would genuinely prefer not to see it. But in a survey image, a slowly moving point of light is a slowly moving point of light. A rock and a rocket stage look identical. So the surveys found this thing whether they wanted to or not, again and again, joined by amateur astronomers observing from Mississippi, Utah, Beijing, and England. And there is one detail in this stretch that deserves its own beat, because it is the most human moment in the entire story. In May 2026, Gray corrected an error on his own tracking page. Working out how badly radar degrades with distance, he had squared 400 and gotten 16,000. The correct figure is 160,000. Squaring the wrong number a second time left him off by a factor of 100. He was told about it by a man named Warren Odom, who had left a comment underneath a magazine article. Gray posted the correction publicly, with thanks, in the list of changes at the bottom of the page. That is what this looked like from the inside, not a mission control room. A web page, quietly revised, maintained by a man who has said he's never been sure whether to call himself an amateur or a professional astronomy, has been his living for decades, but he doesn't hold a doctorate, and in some circles, that's the word that decides it. With 1,000 observations in hand, predicting the path should have been almost trivial. In principle, it nearly was. The motion of space junk is governed mostly by gravity, the Earth, the Moon, the Sun, the planets, and we know all of those with immense precision. Gray has said that if gravity were the only factor, he could probably have told you where and when this object would hit to within a few meters and a fraction of a second. But gravity is not the only thing acting on it. Sunlight is also pushing. This is called solar radiation pressure, and it is the gentlest force in the entire story. The accumulated shove of individual particles of light landing on a tumbling metal cylinder. Over an afternoon, it is nothing. Over months, it becomes something that genuinely moves the object, and it can't be fully predicted, because as the stage turns, it catches more or less sunlight and reflects some of it sideways. The push is mostly away from the sun, but there is always a little pushing in other directions, and it changes as the tumble changes, which is why the object's flicker was never just a curiosity. It was the only handle anyone had on the largest source of error. Now, the orbit itself. The object circled Earth roughly every 26 days on a badly lopsided path. At its closest, it came within about 220,000 kilometers. At its furthest, it swung out to about 510,000. The Moon sits at around 385,000, which means the two orbits crossed. For a year and a half, that was harmless. One of them would reach the crossing point while the other was somewhere else entirely. It happened over and over, and nothing came of it. On August 5th, 2026, they were both going to be there at once. Gray revised his prediction through the summer. In June, it moved 9 minutes earlier and about 170 kilometers northwest. In July, it shifted by a couple of seconds and about 10 kilometers. By August 1st, he had it at 35 minutes and 37.5 seconds past 6 in the morning. Universal time, probably to within a few seconds. Each revision was smaller than the last. The mathematics was closing in on a point, and the point it closed in on was near the crater Einstein, on the Moon's western limb, on the sunlit side, just barely on the near hemisphere, the one we can see. That last detail is the whole problem, and we're about to get to why. The object weighed somewhere between about 4,000 and 4,900 kilograms. The exact figure depends on how much propellant remained, and nobody knows precisely. It arrived at 2.43 kilometers per second, 5,400 miles an hour. There is no air on the moon, and therefore no such thing as a Mach number. But if there were air, that would be about 7 times the speed of sound. The energy released works out to somewhere between roughly 12 and 15 billion joules, which is to say, about 3 tons of TNT, or, if you prefer a more domestic comparison, something like 15,000 sticks of dynamite. With no atmosphere to slow it, it arrived intact and at full speed. But here is what changed how researchers thought about this impact. A rocket upper stage is not a rock. A team at the University of Texas at Austin ran the collision through a high-resolution physics simulation, and one of the supervising professors described the object in a way that reframes everything. It is like an empty eggshell, because it had carried all the fuel, with a dense engine at one end. A solid meteorite burrows in like a cannonball. A hollow shell collapses from its edges inward, throwing up a broad, low curtain of soil, and, in the most optimistic version of the model, a thin, fast spike going almost straight up. A second team, at Los Alamos National Laboratory, ran it through a different simulation built for high strain rate planetary impacts. They let it run for 9/10 of a second, long enough for a transient crater to form, not long enough to settle. Their result: the impact would excavate something on the order of 1.1 million kilograms of lunar soil, around 150 to 200 times the mass of the object that caused it. Most of that debris moves slowly. A small tail of it moves very fast. About half the resolvable fragments fall back within 5 seconds. Only around 2% are still in flight after 30. The largest ones the model could track reached about 1.5 kilometers in altitude, and the smaller ones, too fine for the simulation to resolve at all, almost certainly went higher and stayed up longer. The crater itself was expected to come in between 20 and 30 meters across and around 5 meters deep. NASA put it at roughly 60 feet wide and 12 feet deep. Around it, a continuous blanket of freshly excavated material about 70 meters across. And the most sobering figure had nothing to do with the crater. The maximum ballistic range of the resolved particles was slightly under 1,000 kilometers. On a world with no air, rock thrown out of a 20-meter hole can travel a distance comparable to the length of a country. Nothing was near this impact site to be endangered. But the researchers were direct about why the number matters. It is far enough to be significant for future astronauts and infrastructure across much of the lunar surface. One of the Texas researchers put it plainly: moon rock is very abrasive. Those particles come out at maybe 300 or 400 meters per second, and we are, apparently, going to be operating up there fairly soon. He reached for an Apollo image to make the point: the photographs of Armstrong and Aldrin climbing back into the lunar module, filthy, covered in dust. So we had a 4-ton object, a known second, known coordinates, and a global observing campaign. And the thing we were trying to catch had never been caught before. Ever. By anybody. Impact flashes have been recorded telescopically since 1999. Several hundred of them. The brightest reach around magnitude 3. The most sensitive instruments can pick them up down to around magnitude 11. They last less than a second, which is why observers were advised to shoot at 20 or more frames per second at lower rates. The entire event can happen between 2 frames. But every one of those recordings shares a condition. It happened on the unlit hemisphere. No natural or artificial impact flash has ever been detected on the sunlit portion of the moon. And that is precisely where 20-5010D was heading onto ground, with the sun nearly overhead, next to a surface bright enough to drown almost anything. There was a second problem, and it is more subtle. Flashes are produced when an impactor drives a shockwave into the ground. Natural meteoroids manage this easily. They typically arrive at speeds on the order of 10 kilometers per second and can reach as high as 70. This object was arriving at 2.43. Modeling and laboratory work both show that flash brightness falls off non-linearly as impact speed drops, which makes slow space debris disproportionately dim compared with fast, natural rock. And the reason is beautifully specific. The light output collapses once the impactor is moving slower than the speed of sound in whatever it is hitting. The speed of sound in loose lunar soil is a few hundred meters per second. At 2.43 kilometers per second, the stage would be comfortably supersonic. Shockwave, light, detection. The speed of sound in lunar bedrock is between 1,000 and 2,000 meters per second. Still slower than the impactor, but the margin narrows sharply and the light falls away with it. The predicted impact zone contained both, which produced the widest brightness forecast in the whole affair. From magnitude 3 at the bright end, visible in a modest telescope, to fainter than magnitude 15, meaning invisible to anything anyone owns. Nobody could narrow it down in advance, because nobody knew what the ground was made of at that exact spot. Gray's own confidence moved with it. He said he went from probably to probably not, and more recently to maybe. William Cook, who runs NASA's Meteoroid Environment Office, was blunter. He thought it would be very subtle, very hard to see, if not impossible. But there was always a chance. There was one piece of geometry working in everyone's favor. Because the impact was landing almost exactly on the visible edge of the moon, material thrown upward wouldn't have to be seen against a blinding surface. If it rose high enough, it would clear the edge entirely and appear against black sky. Cook thought the plume was the better target. So did Gray, whose summary of the collective position was essentially a shrug, we don't know, and we should look and find out. Now, this is not the first time we have failed to watch something we ourselves put into the moon. The first artificial impact was Lunar 2 in 1959, a Soviet probe that reached another world by hitting it, and in doing so became the first spacecraft to touch anything beyond the Earth. In 1963, a report circulated that Soviet astronomers had observed the flash. It has never been confirmed. No image, no evidence, just the claim. A possible dust plume from the Lunar 5 impact in 1965 may also have been captured, but it wasn't revealed by the authorities at the time. The pattern holds from there, so we'll move quickly. During Apollo, spent upper stages and lunar modules were deliberately crashed into the moon so that seismometers left by the astronauts could record the vibrations and probe the interior. Those seismic records are still valuable. No confirmed flashes were recorded. The cameras of the era weren't up to it. Japan's Hiten was steered into the moon in 1993, and its flash was caught by the Anglo-Australian telescope. Europe's SMART, one followed in 2006, resolved by the Canada-France-Hawaii telescope, but the brightness was never robustly determined. Which leads to a sentence worth stopping on. Until this week, no actual measurement of flash magnitude from an artificial lunar impact had ever been published. Not one in 67 years of hitting the moon on purpose. Then, in 2009, came the most ambitious attempt. NASA's L-Cross mission drove a spent Centaur upper stage around 2,300 kilograms, arriving at roughly 2.5 kilometers per second into a permanently shadowed crater at the lunar South Pole. A second spacecraft flew through the resulting plume, carrying 9 instruments, then impacted a few minutes later. Scientifically, it worked. They found water ice at a concentration of around 5.6%, and that single result is a large part of why the lunar South Pole is now the most contested real estate in the solar system. But from Earth, observatories trying to watch the flash found it blocked by a small hill on the lunar surface. Ground-based observers initially reported uniform non-detections of the plume as well. The plume was there. Years later, better processing techniques pulled its signature out of data that had already been collected and filed away as empty. Hold on to that, because it happens again shortly. And all of this sits inside a larger blindness. The moon is struck around 100 times a day by objects roughly the size of a ping-pong ball. A meteoroid carrying the same energy as this rocket stage hits it about once every 6 days. In the spring of 2024, a natural impact carved out a crater 225 meters across around 10 times the size of what a Falcon 9 stage makes, blasting out perhaps 1,000 times more material. We saw essentially none of it happen. The oldest possible sighting on record may be from 1178, when a monk named Gervase of Canterbury wrote down an account of flames apparently erupting from the crescent of the moon. For years, that was linked to the formation of a particular crater. Modern work shows that explanation is almost certainly wrong. What those witnesses actually saw remains uncertain to this day. Which brings us back to the morning of August 5th. The campaign was substantial. High-cadence imaging at a 3.5-meter telescope at Apache Point Observatory in New Mexico. Sodium spectroscopy at the 4.3-meter Lowell Discovery Telescope in Arizona. Spectroscopy from an 8.2-meter unit of the Very Large Telescope in Chile. 2 citizen science networks collecting amateur submissions. Observers had been told to run a full practice the night before, under near-identical lighting. In lunar orbit, NASA's Lunar Reconnaissance Orbiter had already acquired baseline imagery. South Korea's Danuri was positioned to pass within a few kilometers of the rocket stage roughly 2 minutes before impact. The moon was a little past last quarter, about 56% illuminated. The geometry was as good as it was ever going to be, and the object arrived on schedule near Einstein crater at around 5,400 miles an hour. Nothing. No image, no flash, no video. Then Chile reported in. The Very Large Telescope, using an instrument built to read the chemical fingerprint of light rather than to take pictures, had been staring at the impact site through the moment of collision. A few minutes after the predicted time, it detected something. Spectral lines. Sodium and lithium gas, hanging above the surface, lasting between 5 and 10 minutes. The sodium came from the moon vaporized soil, kicked up out of the ground. The lithium came from the rocket. That is the part worth sitting with. The last thing that object ever did was announce what it was made of. Lithium contamination from Falcon 9 upper stages had been observed before, in Earth's own upper atmosphere, when stages burned up on the way down. It has a strong, accessible emission line. It is, in effect, a signature. We never saw the impact. We read it. The plume was measured at a few tens of kilometers across. Danuri returned images from before and after, and researchers went back to their other instruments to begin processing data that hadn't shown anything obvious yet, looking for a matching visible signature, which is exactly what happened after L.C. Ross, when the evidence turned out to have been sitting in the files all along. So a crater exists now that did not exist a week ago, 20 to 30 meters across, around 5 meters deep, surrounded by 70 meters of soil that had been buried since the moon was young, now lying open to the sky. Nobody has photographed it. The Lunar Reconnaissance Orbiter passes over that region roughly a week before and a week after the impact, and it has already taken the before picture. Danuri is looking too. When the images come back, and it may take days, depending on lighting, orbital timing, and where the spacecraft happen to be, they will be the first pictures of a hole that nothing living has ever laid eyes on. We know almost exactly where to tell them to look. That was the entire point of predicting the impact site to within a few kilometers in the first place. Not to watch it happen, but to know which patch of a heavily cratered plain to search afterwards. It took months to find the last one, and when they found it, it was wrong. When the Chang'e 5T1 stage struck the far side in 2022, the orbiter eventually returned an image of something nobody had predicted. Not one crater, two, 16 meters and 18 meters across, side by side. A rocket upper stage is a hollow tube with a single heavy engine at one end. It should make one hole. Producing two craters of nearly equal size requires two roughly equal masses, separated from each other, a heavy engine at one end and something comparably heavy near the top. Nobody knows what that something was. The composition was never disclosed. And as far as Gray is aware, China has never publicly acknowledged that the object was theirs at all. That anomaly has never been explained. It is still sitting there, in a photograph, on the far side of the moon, which is exactly what makes the picture we are waiting for now more than a formality. This stage was carrying two landers and nothing else right at the limit of what it could manage. Its mass, its dimensions, and its speed were known in advance. The prediction is a single crater. So, when the Lunar Reconnaissance Orbiter comes back around and photographs the ground near Einstein, that image is a verdict. One crater. And the physics closes cleanly. Everything we thought we understood about how a hollow rocket stage hits a rocky world holds up. Two craters, and a mystery we assumed was a peculiarity of undisclosed Chinese hardware, reopens on an object we thought we knew completely, one with more than 1,000 tracked observations behind it. And that is the quiet reversal at the center of all this. For a year and a half, this thing was junk, the least interesting object in the sky. An annoyance to survey astronomers who would rather have been hunting rocks, tracked mostly by people doing it in their own time, because someone had to. It became a scientific instrument at the exact moment it stopped existing. We knew its mass, we knew its speed, we knew the second it would arrive, and within a few kilometers, where we pointed everything we had at a patch of ground on the bright edge of a world nobody has walked on in over 50 years, and we saw nothing at all. Then a telescope in the Atacama Desert caught two thin lines of light rising together out of a hole that had been open for 4 minutes. One line from the moon, one from us. And the uncomfortable part is that the fix already exists, and it is almost trivial. Use the last of the fuel to throw the spent stage into orbit around the sun, permanently out of the space between here and the moon. It was done for the stage that launched the James Webb Space Telescope in late 2022, parked on a path calculated to avoid hitting us for at least a century, and probably for thousands of years. It was done in November 2025 for the Falcon 9 stage from the Escapade launch. Chinese lunar launches have started doing the same. It is not required, so it is not routine. And it only works for missions that were going to the moon or beyond in the first place. Everything in lower orbit lacks the energy to escape. Avoiding lunar impacts turns out to be the easy problem. Avoiding the things that fall back on us is the hard one. Meanwhile, the traffic is multiplying. More lunar launches, more discarded stages, more dead hardware crossing the paths of landers, orbiters, and eventually crews, all of it moving through the same unwatched volume. This rocket wandered for 18 months. We have been leaving things behind on the moon since 1959. Almost none of it has ever been witnessed. And the newest of them is sitting out there right now, in full sunlight. On the edge of the disk you can see from your own back garden on a clear night, a fresh scar on the only other world in reach, waiting for a camera in orbit to come around and tell us what we did.